In this course, we want to describe the behavior of a hydrogen-like atom. So let me write it down here. Hydrogen-like atom. So why do we call it hydrogen-like instead of hydrogen? Well, because it is a little bit more general than the hydrogen atom. Okay, so what hydrogen-like means is that we consider an atom or an ion that contains an electron. So now let me write it, let me draw it like a point particle. It is not a point particle, of course, because we are going to use quantum mechanics, but at first, let's just try to reason classically, okay? So this is an electron, and hydrogen-like atoms contain an electron in the outer shell, okay? So they have just one electron, and then they have a nucleus. Somewhere here, they have a nucleus, and this nucleus can be made of even more than one particle. For the hydrogen atom, of course, this nucleus would be just a single proton, right? We have a proton and an electron, and this would be the hydrogen atom. And of course, the charge would be zero because the proton is charged positively, whereas the electron is charged negatively, and they have equal charges in opposite signs, so the total charge would be zero. But we can have other hydrogen-like atoms. For example, we could have helium plus. So this is helium with a positive charge of 1, which means that we could get it if the number of protons contained in the nucleus would be equal to 2. So 2 protons in the nucleus and 1 electron in the outer shell, so we would have a positive charge of 1 here. So this is also characterized by the Z number. If you recall, if you know something about this number, this is the atomic number. If you want, it's also coincident with the number of protons contained in the nucleus. So in this case, it would be Z equal to 2. And we can also give other examples like lithium with with 2 plus charges. So it means that Z is equal to 3. And then we could have beryllium with 3 positive charges, which means that Z is equal to 4, okay, because there's also the electron, so it's 4 minus 1 that gives you 3. And then we can also consider boron, for example, boron with 4 positive charges, and here we have Z equal to 5, for example. Okay, and the theory that we are going to describe in the course is capable of describing, of characterizing all these possible atoms, okay? And in particular, we will be interested in the motion of the electron. So we would like to understand how the electron moves, or in particular, the energy levels that characterize the electron. And we will see that the energy levels that characterize the electron are discrete. And that's what we want to derive by using the Schrödinger equation. Okay, but first, now let's still think in a classical manner. And what we will do is we will try to derive the expression for the Hamiltonian of a system. Okay, because the Hamiltonian appears in the Schrödinger equation. Okay, we know that I h bar d psi over dt is equal to the Hamiltonian times psi, where psi is the wave function, of course, h is the Hamiltonian, h bar is the reduced Planck constant. And we would like to derive an expression for the Hamiltonian here and then try to work with the Schrödinger equation, and we will see that we can derive the spectrum of the energy from the Schrödinger equation. Of course, it will take some time, but this is the objective of the course. And first we will reason classically. So we will consider a particle here, which will represent the electron, and this particle will have a mass equal to m2, let's say, and then we will have some nucleus here, then it will be just one particle, a point particle whose mass is m1. Okay, and what we want to do is we would like to derive the kinetic energy of the system here, because this kinetic energy is important because it appears in the Hamiltonian there. Okay, but I will do it in the next video.